Great to have you back in Simple Harmonic Motion, and let's move ahead and explore this topic a little deeper. So if you have an expression for position of a body undergoing simple harmonic motion, it becomes easy to find its velocity. All we need to do is differentiate displacement x with respect to time. So we learned in the last lesson that the position of a mass undergoing simple harmonic motion is x equal to a cos omega t plus phi, where x is the position, a is the amplitude, omega is the angular frequency, t is the time, and phi is the phase angle. So the velocity of such a mass undergoing simple harmonic motion would be nothing but dx upon dt, or the first differential of x with respect to time. So let's go ahead and write what v is. Dx upon dt is equal to the velocity of this mass undergoing simple harmonic motion, which if you differentiate the right side, what you'll get is a omega, because you first differentiate whatever stuff you have inside the bracket, and the differential of cos of this function would be sine omega t plus phi, and you'll have a minus sign as well. So let's put a minus sign over here. So velocity of a mass undergoing simple harmonic motion can be given by this expression. So let's go ahead and plot the velocity of the mass at various times in the same graph in which we found the displacement x, which is this graph. And again, remember that the mass is attached to a spring, which is not shown here. So here we have the mass that has been pulled to the extreme right, and the journey starts from here. In such a case, we also know that phi is 0. Equation becomes v is equal to minus a omega sine omega t. So let's go ahead and write this equation for this particular case, and what you'll get is v is equal to minus 6, because 6 is amplitude, into omega, which is nothing but 2 pi upon the time period, which is 8 seconds. We know that the time period here is 8 seconds, into sine of 2 pi upon 8 times t. So let's go ahead and put various t values to find the various velocities. So at time t equal to 0, you can see that this entire function becomes 0, because sine of 0 is 0. And it makes a lot of sense, because you can see that the mass is pulled to the extreme right, and it starts its journey from here where the velocity is 0. So if you put t equal to 1 second, what you will get is minus 6 into 2 pi upon 8 into sine of 2 pi upon 8, and this comes to minus 3.33 meters per second. And you can see that as time elapses, as the mass starts moving to the left, its velocity increases, because the spring is causing the acceleration towards the equilibrium position. So what I've done is I've already tabulated the various velocities at various times, and this is what I got. So we can see at time t equal to 0, its velocity is 0 meters per second. So let's also go ahead and plot this on the same graph. So at t equal to 0, you can see its velocity is also 0 meters per second. At t equal to 1 second, its velocity becomes minus 3.33 meters per second. And the negative sign essentially shows that the mass is moving towards the left. So at t equal to 1 second, we can say if this is minus 4, this is minus 2, this should be minus 3. So minus 3.33 should be somewhere over here. And at t equal to 2 seconds, it reaches the equilibrium position where we know the velocity has to be maximum and the mass is moving towards the left, and therefore its velocity is minus 4.71 meters per second, which is the maximum velocity. So we'll put at t equal to 2 seconds, velocity is 4.71 meters per second. And if this is 5, then 4.71 should be somewhere over here. And then we find at t equal to 3 seconds, the mass has gone beyond the equilibrium position and its velocity is minus 3.33 meters per second. So if we plot minus 3.33, it should be over here. And then at t equal to 4 seconds, it becomes 0. So the velocity here is 0 meters per second, because you can see at t equal to 4 seconds, it's reached the extreme left position where the velocity becomes 0 because the spring is compressed, totally compressed, and then it starts pushing the mass again towards the equilibrium position. So at t equal to 5 seconds, we see that its velocity now becomes plus 3.34 meters per second because now the mass is moving towards the right. So we will put at t equal to 5 seconds, the velocity is 3.34 meters per second. So it should be somewhere over here. And at t equal to 6 seconds, its velocity is 4.71 meters per second, which is again the maximum velocity, because you can see at t equal to 6 seconds, the mass is again come back to its equilibrium position where the velocity is maximum. So it should be somewhere over here, 4.71 meters per second. And at t equal to 7 seconds, once again, its velocity is reducing because it's moving towards the extreme right. And as it moves from equilibrium position to the extreme right, we know that its velocity will keep reducing. So at t equal to 7 seconds, the velocity is 3.33 meters per second towards the right, and therefore positive. And 3.33 should be somewhere over here. And at t equal to 8 seconds, we can see that it has once again moved to the extreme right position and completed one oscillation. So we'll put at t equal to 8 seconds, its velocity is 0 meters per second. So we'll put a dot over here. So this is just a rounding error. You can see minus 0.01, which is probably a rounding error. And here also 0.01 is there. It should be 0. So let's go ahead and connect these dots and see what we get. So this is the kind of graph we've got for velocity of this mass. And well, if you keep putting more x and t values and make the graph further down, let's say to 16 seconds, 24 seconds, and so on and so forth, this is the kind of graph you will get. And you can see that the relationship between velocity and time of a body undergoing simple harmonic motion is also a sine wave. Well, if you've noticed, the maximum velocity can be a omega, because you can see that the sine of any angle cannot be more than 1. So the maximum value you can get is a omega. So in a way you can say that the amplitude of velocity, and let's write it over here, that the a omega. So the velocity cannot exceed this value. Well, let's move ahead and find what is the acceleration of the mass at various times. This mass is subjected to a varying force offered by the spring, and therefore its acceleration also changes. Well, if we differentiate velocity function with respect to time, what we'll get is acceleration, or we can say that a is equal to dv upon dt, or the acceleration is equal to dv upon dt. So let's go ahead and write that. So we'll write acceleration a is equal to dv upon dt, or the differential of velocity with respect to time, which is equal to d upon dt of velocity, which we have found as minus a omega sine omega t. Well, if you start the mass from any position other than the extreme right, you'll also have the phi angle, or let's go ahead and put this as omega t plus phi. So if you differentiate this, what you get is a equals minus a omega square, because you get another omega from inside, and this changes to cos of omega t plus phi. And we know that for this particular case, a would equal to minus a omega, we can write as 2 pi upon 8, which is 2 pi upon capital T, or the time period. And we know that the time period is 8 seconds, whole square into cos of omega t. Again, omega is 2 pi upon 8 into t, and phi we know is 0 when you start the journey of a mass from the extreme right. And now if you put various t values in this equation, you'll get the acceleration of this mass as it moves from extreme right to the left and then back to extreme right. And I have once again tabulated all the acceleration values for various times starting from 0 second right up to 8 second, and this is how it looks. So you can see that for various t values, you have the position values, which is represented by x, and then you have the velocity values, which is this column, and this column over here gives the acceleration values for this mass at various times. So you can see at t equal to 0 seconds, its acceleration is minus 3.7 meters per second square, and it's a maximum acceleration, and which seems a lot logical because this mass is pulled to the extreme right and the spring is pulling it to the left with full force or maximum force, and therefore the acceleration also needs to be maximum, and it needs to be negative because it is getting pulled in the left direction. Likewise, at t equal to 1 second, its acceleration is reduced a little, but still it is in the left direction, and it's reduced because the spring is now not as much pulled as it was when the mass was at the extreme right position. So let's go ahead and plot the acceleration values also in this graph, just the way we plotted the velocity values. And what you'll get is at t equal to 0, the acceleration is minus 3.7, and 3.7 should be somewhere over here. At t equal to 1 second, it is minus 2.62. So 2 is over here, 3 is here, so it should be somewhere over here. At t equal to 2 seconds, it becomes 0. So the point should be over here, and makes a lot of sense that at t equal to 2 seconds, the acceleration is 0 because the mass is in its equilibrium position and there is no stretch or pull in the spring. So there's no force acting on the mass, yet it tends to move towards the left because of the momentum it has gathered or the velocity it has. So at t equal to 3 seconds, we see that its acceleration becomes 2.62 meters per second square. So let's go ahead and plot this at t equal to 3. Its acceleration is 2.62, which should be somewhere over here. And you can see now the acceleration is in the right direction because the spring is getting compressed, and therefore the spring is pushing the mass towards the right, and therefore the vector direction is changed. And then at t equal to 4 seconds, we can see that the mass is in the extreme left position and the spring is totally compressed, and therefore the spring is pushing the mass towards the right with an acceleration of 3.7 meters per second square. So at t equal to 4 seconds, we plot this as 3.7 meters per second square. And you can see at t equal to 4 seconds, it starts its journey to the right, and at t equal to 5 seconds, we see the acceleration is 2.62 meters per second square, which should be somewhere over here. And we see at t equal to 6 seconds, it's once again in the equilibrium position, and therefore there is no force acting on it because the spring is not stretched or compressed. So we see at t equal to 6 seconds, its acceleration is 0. So we put a dot here. Again, this is a rounding error. This should have been 0. Then at t equal to 7 seconds, we see that the mass has moved to this position, and obviously the spring is once again pulling it to the left, and therefore the acceleration is negative. So let's go ahead and plot at t equal to 7 seconds. It is 2.62 meters per second square, which should be somewhere over here. And at t equal to 8 seconds, once again the mass is getting pulled with full force towards the left because it is at the extreme right position, and the spring is pulling it with full force. So at t equal to 8 seconds, we put the acceleration as 3.7 meters per second square. So this would be the dot. So let's go ahead and connect these dots and find what kind of curve we get. So this is the curve we'll get for acceleration. So a little inaccurate. Let me try to draw it again. Yeah, this is better. So if you were to again plot this for more values of t, this is the kind of graph you will get. Well, you can also see that the maximum value of acceleration you can get is minus a omega squared, because cos of any angle cannot be more than 1. So in a way you can say that, let's write it over here, amplitude of acceleration is equal to a omega square. Okay, let's rewrite this equation in this fashion such that a is equal to minus omega square a times cos of omega t plus phi. Now what you can see is that a cos omega t plus phi is nothing but the position x, which I've written over here as a cos omega t plus phi. So we can go ahead and write a as equal to minus omega square x. And this equation is a classic simple harmonic motion equation. So if you find any equation that relates acceleration and displacement in this way, you can conclude that the motion under question is simple harmonic motion. So the equation would have acceleration vector always opposite to the displacement vector. You can see the negative sign here, which essentially indicates the fact that displacement is opposite to the acceleration or the force that is causing the acceleration. Also, the equation would be related by a constant omega square. So with this understanding, let's see simulation of a mass under simple harmonic motion and see how displacement x, velocity v, and acceleration change with time. Try to see first the change in velocity against position x, and then observe the acceleration against position x. And while you're observing, try to relate to what is actually happening at a physical level. That is, just imagine what is happening to the mass as it is moving to the right and to the left, the spring force acting on it, and how the mass is behaving. Remember, the more you imagine and visualize, the better you'll understand physics. So here you go. So if you like this video, go ahead and give it a thumbs up, and please do not forget to subscribe to this channel for many more interesting videos.